everyone. Today we are going to present about electrode deposition, that is also known as electrochemical deposition or electroplating. This presentation is brought to you by Group 2. I am Yuequan. My teammates are Haslam, Jiddan, and Brandon. So what is electrode deposition? It is a method of additive technique that utilizes electric current that act as a medium for the deposition process to occur. Electrode deposition is an alternative method to physical vapor deposition and chemical vapor deposition. It is a bottom-up process, which means that it builds up the material from a smaller size to a larger size. And finally, electrode deposition is one of the simplest and oldest technique to synthesize thin film coating of metal oxides. Electrode deposition was invented by Italian scientist Luigi Valentino in 1805, which he connected a wire between a solution of dissolved gold and a battery named voltaic pearl that was also connected to a metal object. When the electric current was flowing across the circuit, the gold was attached to the surface of the metal objects, hence creating a shiny thin film of gold coating. However, electrode deposition was stopped by the French Academy of Science from emerging to this industry for 30 years. And in 1839, two scientists from Russia and Britain parallelly found out that the copper deposition was able to use for the coating of printing plates. Therefore, in the early days, electrode deposition was mainly used for decorative purposes. Only until 1950, more electrode deposition metals were developed and discovered. For example, it includes nickel, gold, zinc, and tin. Currently, electrode deposition has the general uses of decorative purposes for the preparation of nanomaterials, and electrode deposition could also be used to act as a protective layer to avoid corrosion from occurring. And finally, electrode deposition can be used for functional purposes. For example, it helps to improve the conductivity or resistivity for certain materials. With these general uses, electrode deposition excels in industrial roles such as automotive, electronics, aerospace, jewelry, and fashion items, medical devices, and some parts of machinery. The fundamentals of electroplating takes advantages of the electrolysis process, which is shown in the diagram right here. With the electric current entering the system, a potential difference will be created between the two, causing reduction and oxidation to occur, which is redox reaction. Deposition on the substrate is done through the reduction of cations, which is the positive ions of metals, to be deposited on the substrate through the use of electric current. And now I will be passing the presentation to Jiddan.
As we know, processes that are typically applicable at the macro scale may not always be easily applicable at the micro and nano scale. Electrode deposition faces a few challenges in being applied to the micro and nano scale, mainly achieving uniform deposition and precise thickness of deposition. Because at such small scales, to overcome these challenges, precise control over process parameters and setup designs that improve our control over the process are required. The first and most conventional electroplating procedure for the micro and nano scale is through mask electroplating, where we use photolithography masks to selectively deposit the metals through conventional electroplating procedure. The process is similar to the ones used for other deposition procedures, where we go through promoter and resist coating, necessary bakes, resist exposure and development, and electrode deposition before stripping the resist through liftoff procedures. It's conventional and simple, but while the deposition process can be done outside a clean room, the masking procedure can't, which produces some issues. After creating the necessary masks, the actual electroplating procedure can be adjusted based on our needs, one of which is using pulse electroplating, where instead of directly flowing the current for a set duration, we cyclically pulse the current in an alternating fashion to allow for precise controlled deposition. The setup may also be changed by using barrel electroplating, where we use a barrel cage such as the one shown in the picture, albeit at a smaller scale, and the current is flown through the barrel cage while the barrel is being rotated and immersed in an electrolytic bath to produce efficient and uniform plating process at the cost of quality and precision. The masking into plating procedure may be considered quite tedious for mass production. Hence another method is produced, namely the use of instant masks. The desired masks for each layer of deposition can be engraved directly on an anode. Therefore, instead of having the mask on the substrate cathode and a separate anode, the mask can just be pressed onto the substrate and immersed into the bath with current for deposition, and after that the mask can just be removed, which is a much simpler process. For complex layered electrodeposition, such as when trying to build up a precise layer of structures, a single large anode metal can be etched into multiple submasks, such as shown in the figure, separated by an elastomeric insulator in between each masks. And we can do repeated electrodeposition by moving from mask to mask, and this process is called EFAB, or electrochemical fabrication. The setup for a tabletop EFAB is typical to a typical mask aligner, though instead of having a mechanism for UV exposure, we have an electrolytic bath in it, where the current is flown into the substrate, which is placed vertically, and the substrate is alternatingly pressed onto different part of the masks on that large anode metal for repeated selective electrodeposition. And in this process, a select sacrifice material is selectively deposited using an inverted mask before the actual desired material is blanket deposited in the bath without mask contact. And because this layer will be uneven, it will be planarized first, and this process will repeat until all layers are formed before the sacrificial material is wet etched away, leaving only the desired structure that we want to create. In electroplating, key parameters exist to control the deposition rate and thickness as well as the quality. The duration of the process determines the resulting thickness, while we can control the current density and exposure to current at each cycle, where we can determine the rate of deposition. The pH level, metal ion concentration, and temperature of the bath can also positively affect the rate of deposition. On the other hand, the quality and uniformity of deposition can be determined by the cleanliness of the setup and surface before starting the process, as well as surface preparation procedures such as adding additional layers beforehand for improved adhesion. Agitation of the electrolytic bath, such as the one we see motivated by the barrel electroplating setup, will improve the rate and uniformity of the deposition as well.
Here are some applications of electrodeposition at the micro and nano scale. On the micro scale, electrodeposition is used for microelectronics, microelectromechanical systems, and for developing photonics and optoelectronics. As for the nanoscale, it is used in biomedical applications, nanofabrication, and nanomanipulation and energy storage and conversion. Let's go in depth on how electrodeposition is used for each one. In the microscale, for the uses of electrodeposition in manufacturing microelectronics, it is used for circuit patterning to create micro-sized circuit patterns on silicon wafers for integrated circuits. It is used for metallization for interconnects, where it deposits thin layers of metal such as copper for electrical interconnects in microchips. And as for semiconductor device fabrication, it makes microscale transistors and diodes on semiconductor substrates. In MEMS, electroplating is used in electroforming of microstructures, which forms microscale parts such as gears, valves, and actuators for MEMS devices. It is also used for plating metal layers on microscale sensors and switches. As for photonics and optoelectronics, electrodeposition is used to create microscale plasmonic waveguides and sensors for optical communication. Now let's have a look at the nanoscale. The uses for electrodeposition in the nanoscale are used for biomedical applications such as nanoscale drug delivery system, biosensors, and tissue engineering. For drug delivery systems, electrodeposition can be used to capture nanocarriers for targeted and controlled drug release at the cellular level. In biosensors, it is used for fabricating nanoelectrodes for detecting biomolecules with high sensitivity and specificity. As for tissue engineering, it is used for building nanoscale scaffolds with precise architecture for directing cell growth. In nanofabrication and nanomanipulation, electroplating is used for nanoscale patterning for advanced lithographic processes such as EUV lithography. We are also able to manipulate individual nanoparticles for precise assembly in nanoscale devices using electroplating. And as for energy and storage, electroplating helps fabricate electrochemical capacitors, which are nanoporous electrodes with high surface area for energy storage. It is also used for depositing nanomaterials like lithium compounds for high-performance batteries. And lastly, it creates nano-sized catalysts for efficient energy conversion in fuel cells. I will now pass on to Haslam.
Electrode deposition is just one of many routinely used deposition techniques used in micro and nano manufacturing. Common methods used to produce small-scale layers can be split into two broad categories: physical vapor deposition and chemical vapor deposition. Physical vapor deposition, or PVD, involves the application and adherence of particles to the component surface through physisorption. This relies on van der Waals forces, which are relatively weak and make for poor layer adhesion. Thermal evaporation and sputtering are perhaps the most common PVD types. The former is very useful in producing uniform layer thickness in a directional manner that doesn't coat sidewalls, which better allows for subsequent lift-off processes. The slow evaporation of tiny particles that don't transfer much energy means that thermal evaporation is a low-temperature technique, much like electrodeposition, which permits use in heat-sensitive substrates. Thermal evaporation is also less limited than electrodeposition when it comes to material choice. While it is a poor choice for coating compounds, it's also not restricted to just coating metals. However, it's quite unsuitable for creating very thick layers like electrodeposition is. Sputtering PVD is far more suited to producing thicker layers, which it can also do conformally for the purpose of insulation. Sputtering allows for a wide variety of coating materials and compounds, gives better adhesion, and applies material faster than thermal evaporation, but it does so by losing layer purity due to the use of high temperature plasma. Both methods are largely restricted to layer thicknesses less than a few hundred nanometers without excessive process time, whereas electrodeposition is completely applicable for plating several micrometers thick while retaining sufficient layer quality and comparatively short duration. This means electroplating may be a better choice for making sacrificial layers. Chemical vapor deposition, or CVD methods, get around the weak layer adhesion issues of PVD by instead relying on chemical bonding. CVD methods involve chemical reactions at the component surface of a gaseous phase, which also allows better conformal application through rough textures or complex geometries. In its simplest form, atmospheric CVD is a comparatively low-tech method that lends itself to applying thick layers. This and its higher rate of deposition are traits shared by electroplating. So there may be some overlap in application between these two methods. While suitable for insulation layers in some cases, the lower purity, because the process doesn't take place in rarefied air, might be unacceptable, as it can lead to short-circuiting. Low-pressure CVD takes place at highly reduced pressures, and a result can produce exceptional layer quality in conformal coatings, adding in its ability to process many wafers at once. Much like numerous electrodeposition techniques, LPCVD is a high-quality process. However, it does require very high temperatures, which limit its use to heat-resistant materials. Plasma-enhanced CVD can circumvent the temperature restriction by using high-energy plasmas to provide the necessary extra energy for deposition. But for near room temperature applications, this results in added impurities or damage to the layers and substrate. CVD methods are well suited to producing strongly bonded layers of very high quality, particularly oxide layers. However, the required trade-off between LPCVD's very high quality and PECVD's low temperature is one that electrodeposition doesn't have to make, which is an interesting advantage. However, electroplating does come at the cost of reduced controllability of layer thickness and uniformity at the micro and nanoscale, as we mentioned before. Much like other techniques, minimizing impurities is a crucial factor in determining layer quality and strength of adhesion. For electroplating, cleanliness of the electrolytic bath, removal of any oils or particulates, for example, is quite key. It's worth noting that for micro and nano manufacturing applications, electroplating will typically be used with another deposition method. Given the electroplating process requires a conductive base or seed to grow layers, the placement of a seed layer via a PVD or CVD technique should be required as is. Therefore, it's less pressing that electrodeposition needs to outperform these other methods across the board. The requirement for a conductive base upon which the electrodeposition grows also means that electroplating can be applied locally through calculated use of mask patterns. Unlike many other deposition techniques, which apply particles to form layers over an entire substrate or wafer area, electroplating will only proceed where the seed layer exists. Resist can be used to ensure electroplating only forms metals where desired, and also allows for the production of intricate microscale shapes in some cases. Comparative simplicity also makes it an excellent option for protective external covers that resist corrosion, moisture intrusion, or chemical damage to internal electronics. Here, concerns of potentially poorer layer quality compared to some other processes can be outweighed by sheer plating thickness, while the fast deposition rate also makes for shorter processes and hence more streamlined mass production. These use cases are also sacrificial coatings. Electrodeposition may fit well into a niche use case alongside other methods, as it's comparatively good at applying thick metal layers or more bulky metallic components of microscale devices, while remaining a less technologically advanced and prohibitive process. These benefits are likely part of the reason for electrodeposition's increasingly widespread use in micro and nano manufacturing. When considering process flows holistically, choosing electrodeposition where applicable can allow for a simpler, faster, and less costly production. That concludes this look into electrodeposition and its merits. We hope this has been informative. Thank you.